I'd like to thank, first of all, your virtual presence in this plenary talk. It's the last talk of the day. And it's a great pleasure for me to introduce our speaker, Professor Renato Dupke from the National Observatory in Rio de Janeiro. Renato is professor of physics in the Department of Astronomy, professor of astrophysics in the Department of Astronomy at the National Observatory. He's an expert on extragalactic astrophysics, work on high energy astrophysics, the physics of galaxy clusters. So, and now he's since a few years now he's the PI of the Jpes in Brazil. And co-director of this collaboration, and he's telling us today the status of this collaboration, and it's important for the Brazilian community. So, Renato, I'll pass the word to you.
Okay, thank you. Let me get the volume a little higher. All right, so you can see my screen fine, right?
Yes, very well.
All right, good. So you already saved me 30 seconds of presentation. So my name is Renato. So I'd like to first of all thank the committee, the inviting committee, for giving me the chance to talk a little bit about this project that has been going on for a pretty long time. Actually, I'm very happy to see it working. And parts of it are already actually producing a significant number of results, and I'll brush a little bit on that. And also to thank, like João just mentioned, he and Sergio Fontes started, and João, so both of them deserve big thanks from us in the Jpes community for making sure that the project was, our camera, the Brazilian camera, was finished in times of difficulty, financial difficulty. So Jpes, as you can see here, is a Spain-Brazilian Hispano-Brasileiro project. And Jpes stands for Javalambre-Physics of the Accelerating Universe Astrophysical Survey. Javalambre is the name of the place where an observatory was created, built, and the infrastructure by the Spanish folks there. Was specifically created for Jpes. And this is one of the images. There are two telescopes, and I'll show you a little bit more about this in a few minutes. My talk is going to be a little more observational, perhaps, than the other ones. So there are four founding institutions for this. CEFCA, which is the Centro de Estudios de Física del Cosmos de Araguán, which is an institute that was built also for Jpes, and it's a data center as well. And it's in a city called Teruel, which is near the mountain, and I'll show to you in a second. This is in Spain, and the Instituto de Astrofísica de Andalucía in Granada, where the main person that gave the original idea, 12 years ago, was from. And in Brazil, the National Observatory and the IAG in São Paulo. So the collaboration, the representative of the institutions are here: Javier Senaro, myself, Pepe, and Raul Abramo, and Silvia Bonali, and I share the scientific directorship of the project. So the basic idea for Jpes is quite simple, is to transform a real spectrum, into, or recover this from this, what we call spectrophotometry, which is a spectrum made with a ridiculously large number of filters. So there's just an image showing, this is basically the whole idea. The idea of photometric redshift, which is, everybody probably knows, is not new. It's quite old, actually, and people have been trying to recover the redshift of astronomical objects with broadband filters and a little bit narrow band filters and so on. And in 2009, Jpes is characteristically unique in that sense, because we use this technique, photometric redshift, to a level that has never been used before. And it's thanks to Narciso Benitez, Chicho Benitez. In 2009, he published a paper showing how much could you improve your redshift precision if you increase the number of filters that you have. Because traditionally, photo Z is done with 4 filters, 5 filters. You see this everywhere, and even big surveys like SST will have a limited number of filters to be able to get photo Z. And this actually created a lot of discussions at the time, because there was this, the astronomers did not want to compare real spectrum, real redshifts with the photoz's, because they were significantly worse. However, depending on the configuration that you have, and that's what Chicho explored, this is a picture of his paper at the time, and was significantly more exaggerated than we have nowadays. We actually have a better result than this. And he showed that after 5, 6 filters that you have, your precision, the redshift precision, increases fantastically, very, very, very fast. And this was up to 40 filters. And we have actually one of the co-projects that appear together with us is doing a very small size part of the sky with 40 filters. And some of the Spanish group, including Chicho himself, they tried a survey with 20 filters before, and they kind of showed the proof of concept that this was an improvement. In Jpes, we are actually quite about here at 54 narrowband filters. Okay. This combined with a clever introduction of odds, Bayesian odds, to determine what is the best redshift when you have multiple peaks in your photo spectrum, allows us to get, for a significant number of galaxies, what is needed for the main motivator of the survey, which I'm going to talk in a second, which is the measurement of baryonic acoustic oscillations, which is to get to 0.3% in redshift. That's 900 kilometers per second, basically. And with the odds, you can actually sacrifice a lot of galaxies that do not have very good odds. The odds basically is the ratio of the area of the best peak, or the peak they're considering, with all the area of the other peaks there. And they can be a function of many things. You can do priors with respect to the magnitude, the type of galaxy, and so on. But if you throw them out, the bad ones, you lose galaxies, but you basically lose photometric depth, but you increase photo redshift depth. And so you can go very deep, and you can get to redshifts of 1, you can get to more than that. Our initial experiment showed we can get more than that, and with a significant precision of 0.3%. So well, yes, like I mentioned before, the original motivator, and because at the time there was, and still now, right, dark energy is still one of the main problems that we have. So measurements getting this kind of precision redshift was enough. It actually was designed to be enough to be able to measure the baryonic acoustic oscillations. And I'm sure that most people here know much more details about BEOs than myself, but they are caused by initial perturbations of density prior to the universe become recombined. And due to the difference of interactions between baryons and dark matter, you have at the end statistical sliced enhancement in the creation of structure at a particular distance of 150 megaparsecs. This is 100 because this is H1 here. So this is a very tiny one. It has been measured. The correlation function has been measured by Eisenstein in 2005, and this was known at the time. However, with this precision redshift, you can actually get the radial direction, right? This is not a three-dimensional statistical structure. So more or less the thickness of the BAO is about 12 to 15 megaparsecs. So you need to have a 0.3% to be able to get that. And the advantage for this is the angular size distance, and this is the radial distance as a function of the Hubble function, evolution function, is that what was measured before is more tied within the errors to get what you want, which is the omega, the parameter of the equation of state of dark energy, which is only one integral away from the HC. So if you can get HC directly, you get an improvement in your precision from measuring the equation of state parameters of the dark energy. And this is what this is a slide from Chicho's paper. At the time, this is just an example. This is the relative error that you get. This is the angular size distance. This is the age, okay, the Hubble function. And this is the relative errors for W from dark energy. So if you want to get something at about reduce 4% error, and you use the angular size distance using this standard statistical ruler that you have, to get this, you'd have to go very, very deep, okay, more than redshift 1 to be able to get to this precision. So, and if you use directly the radial BALs, you can get to this basically in the, well, I would say for astronomers, this is already intermediate redshift. There's a lot of interesting stuff there, but for cosmologists, it's near, low redshift, so 0.3, 0.4, and if you got your 0.6, you're already past and you're below 4% level. So that was the basic motivation. How do you do this? So one way of doing this is to get a lot of big field of view telescopes and get zillion fibers there. At the time, 1,000 fibers was pretty much what was feasible. And there were some people trying to do, trying to increase to 2,000, 3,000 fibers. Was extremely expensive, very complicated technology. You have to have the robots changing the fibers all the time, and you have to choose your galaxy beforehand, right? So you are selecting the galaxies that you're aiming at to get the results that you want. So with this improvement in the precision of photo Z, it was clear that you could do a different approach for that, which was to have your large field of view. That's our camera. Okay, those are very, very large CCDs. They're probably they are effectively the largest CCDs in existence. And putting a camera that is very big. The camera that we did is not the first; it's the second. Was the second, but Penn Stars made a copy of the first one. So now it's what, the third biggest camera in the world. And get your zillion of different filters here. So you can get your pseudospectra. We call this the J spectrum. If you do this with our system has more than 4 square degrees. And if you do for 4 square degrees, it's equivalent to a 5,000 fiber multiplex spectrograph, right? To do pretty much the same thing. Except that it costs 10 times less, or even more than 10 times less. The camera itself, if you count the whole Jpes project, I have to count the observatory that was built in Spain, but this is not, I'm not counting that as part of the instrument. And this is perfect for countries like Brazil and Spain, to do this. We don't have the same amount of money that the super rich countries have, and that's why we started doing it. So that's what Jpes is. We aim at covering more than 8,000 square degrees, and then probably you can get all the results that you are aiming at with that. And perhaps after that's changed to another survey more specific to other things, perhaps not even cosmology. And this is the configuration of the filters. They are spaced 100 angstroms from each other. Nowadays, technology of filters is really, really impressive. You can get very flat transmission in this fields. In these filters, they're very homogeneous. And this is just simulation of a galaxy, how you'd see this galaxy redshift of 1. This is a luminous red galaxy. People use different terms in astronomy: luminous red galaxy, bright elliptical galaxy, so on. This is the red galaxy. They have this 4,000 angstrom break, but redshift of 1 would fall about here, and that's what you see, the pseudospectrum. And then you can do your science. The project, once it starts, it's supposed to get this level to be every 7 years and get the Baronic acoustic oscillations. And we're talking, originally it was intended to the nearby BAOs, but now we can actually see that we can do more. We can do BAOs at very high redshift. And I'll explain this in a second. Except that one advantage of Jpes is that instead of having the fibers, each pixel, and it's a 1.2 gigabit pixel, gigapixel, right? each pixel gets a full pseudospectrum of the sky, not just the galaxies they're aiming at. If you're looking at, oh, we want red galaxies, you get the blues too. And you get the other galaxies. You get quasars as well. You get stars there in the middle. You get everything. So Jpes was an interesting project because, and especially when I present this at ON, it was well received because you can, people that work in stellar astrophysics can do science with Jpes. People that work with even asteroids can also use Jpes, and on top of the cosmology that we can do. So where it is, what is it? It's in Spain, in the smallest autonomic republic of Spain, state, which is Aragon, and that's the capital of the smallest place, which makes it the smallest capital as well in Spain. So it's a very interesting place, and used to have people complain that this place was abandoned, the roads would not be there, and so on, but made it really great for astronomy because it's one of the darkest places in Western Europe. So it has a very nice seeing of 0.7 arc seconds, and it's very good for astronomy. So I mentioned before there were two telescopes there. The main telescope is this one. Is a 2.5 meter telescope, and astronomers call this étendue. It's a very large, it's specifically built for surveys. It's a very large field of view. It's 7 square degrees, but in practice, because the camera, we want the light that falls in the CCD, ends up being 4.5 square degrees. And a second telescope that's much smaller, it's 0.83 meters, also large field of view of 3 degrees, that was originally intended for photometric calibrations of the big one. But it has only 12 filters instead of 56 filters. They realized that they can do also a lot of science with this thing, this little thing. And so this became the Javalambre-Physics of the local universe survey. And right now has been working since 2005, and it's mapping the local universe. It's not very deep, but it gets also photospectra, not with the precision of Jpes, but can get close to 1% or something like this. And this is the configuration of filters that they have there. They have some that coincide exactly with the Jpes ones for calibration, and they have some other ones that intended to measure specific lines for astrophysics of galaxy stars and so on. So this is the first data release was done in 2019, and last year we released the second one, and we're covering pretty much the same footprint as Jpes, which is pretty much everything that can be usefully observed for extragalactic astronomy and cosmology, or initially in the northern sky. And also a copy of Jpes was built here in the southern hemisphere is in Chile, and also is, you must have heard about this, it's called S+, and it's pretty much analogous to that for the southern hemisphere. This for you to have an idea, this is a nice picture to have an idea of the size of this of the CCDs, and that's the one CCD there is in Jpes. Okay, Jpes has 14 of those. Jpes has 1, and this is the focal plane of the main camera. Those are, well, I'm sure that people here don't care very much. Oh, actually, maybe some people here instrumentalists from the talk I just heard, but wavefront sensors and some other devices in the camera. And you just can't ignore this. And what matters here is that we got a very nice readout noise for observations, and it's 0.23 arc seconds per pix for a 1.2 gigapixel camera. This is just so you know that the system of magnitudes, for those who like magnitudes, we get to this the different limiting for each one of the filters, and it goes about between 21.5 and 22.5. This is the narrow band, and this is the broadband. The broadband can go, of course, deeper. And there are 5 trays, basically, 4 for narrow band and a 5th tray for the broadband. This was the predicted one. But while we were waiting, oh, actually, I can show you. Let's see if this plays. This is the view from the actual observatory. It's a real view of light. This is the main telescope. The Jpes, the other telescope, is right here. This is a view measurement, and you have most of the structure is actually underground. This was all built for the project. And it even has some geothermal energy supply for the things. This part here is some of the astronomer houses. It's supposed to be fully robotic, but you have to have at least 2 people there to monitor the system. And when it gets winter there, it gets relatively cold, sometimes to minus 40 degrees or something like that. So you have to have all those 2 people because then they get stuck and freeze. So this is the footprint for Jpes. This I should thank Alessandro Geracliti, who is our current coordinator for the survey strategy. And I was saying, while we were waiting, and most of the results I'm going to show to you comes from this particular mini project, we're waiting for the camera to get done. So we built another camera, a smaller camera, to put in the telescope with the idea of testing, doing some proof of concept for Jpes, and with one CCD only, one of those CCDs, by using the big field of view and start commissioning of the telescope. Maybe it would be faster if you start earlier, you know how the telescope works, the issues you have to do, and so on. So this CCD is, by the way, 9.2 by 9.2 kilo pixels, each one of them. So we chose a few fields to observe and do this test. Okay, we call this nowadays mini Jpes, and we have some other secondary fields. The total of this was about 1 square degrees only, with all the Jpes filters to test it. So the filter that was chosen, I will show you in a second, is called AGES, or the Deep 2 growth strip. And we also took one field that is important right now because of the joint project with JWST, which will be launched in December with Jpes. So this is the field, the main field there, and this was chosen because we wanted a field with a lot of spectroscopic redshifts, so we can do the photoses and see if they're really as good as it was intended to be or predicted to be. And this field has a significant number of spectroscopic redshifts, but also has a lot of different coverage. This is a famous survey field. It has Spitzer, the satellite, the infrared, Hubble. It has CFHT-LS, the Canadian-French Hawaii telescope, Chandra in X-rays, VLA in radio, and deep galaxy in UV, and so on and so on and so on. So it's an interesting field to do that. So that's what we did. This is Subaru camera, has other optical things there. Alhambra was a previous 22 filter survey that was done analogous to Jpes, but smaller in scope. And there were 4 pointings basically there. So the total area is about 1 square degree, okay, for this. So in 1 square degree, there were 65,000 objects selecting the R band, 600K objects selecting individual bands. And this data is actually publicly available. We made it publicly available in 2019. And a lot of all the papers and all the things I'm showing you now, they're coming for Jpes, they're mini Jpes, this data here. And some of it is from Jpes from some time ago. So this is the field again. I just reverted the direction here. And you can see some nice, those are Milky Way stars. There's an F star, co-star. You can see the nice spectra. This is a quasar, and you can see the lines. You can get the lines here. And 12,000 galaxies with particular lines that people can determine the redshift. And not just that, the chemical composition, you can actually, as I'm going to show you some of the results, you can study the evolution of galaxies with redshift and even the internal structure of galaxies based on this, because, and especially with the really amazing advance of artificial neural networks, or CNNs, that allow this massive amount of data to be used to detect the lines with an incredible precision. Oh, okay, if you have time, let me show you then. It's better than to show spectrum one by one. This is a little movie that was made by Silvio Bonalli with a student who did a master thesis on this. And basically that is the field. I don't know, it's an animation. I haven't put a soundtrack yet. But the data here in the back is real. So you can see there can be some different spectra, J spectra. Okay, so white dwarf. You can see the lines, H alpha, H beta, H gamma. Those are different stars. A0 is a hottest star, F0 a red star. Maybe we can skip directly to the galaxies if you get bored. If anybody gets bored, let me know. Just skip it to the more cosmological. Oops, sorry. Pulsars are great because you see many lines there. Magnesium, sodium, titanium oxide, or something like that. Resolved cell populations, that says Z 0.07. And this is the information you get, including the famous O2 for those who like galaxies. It's a very informative line. Okay, let me skip a little to the more interesting cosmological, perhaps. Galaxy evolution, galaxy large distances. Okay. Let's go to the next one, which is actually more relevant cosmologically, both of them. Okay. That quasar 1.7, very nicely seen. Another one, 4.3. And this is my preferred one because I like clusters of galaxies. I'm a high-energy cluster of galaxies fan. And this is the most massive one at 0.28. And probably it's going to be like a couple of works of papers on this, perhaps more, because it's interesting. Let me just go back here. It's an interesting cluster because we suspect there's a possibility this is a line of sight. The configuration is really bizarre. So maybe a line of sight, a plane of the sky frontal merger, which if it is the case, so we can use this to test things like the cross-section of self-interacting cross-section of dark matter. And that's an interesting thing. So I'm gonna just go to, so you can see who did, Sarah Perez Sanchez, she's a student of Cyril Bonali who is doing this. It's a cool thing. So with the odds, so this is the initial results. This is the results you have. This is actually a little better now because this slide's a little old, but this is the precision of the photos you can get. That's the 0.3% they're aiming at. And depending if you want completeness of 100% or 20%, depending on the odds, you can go deeper. Okay, so if you reduce 20%, you can go to magnitudes that almost 23. And so you can go really deep and increase your volume of objects there, even though you lose a number of galaxies. But if you have hundreds of millions of objects, you can afford to do it. That's a comparison between the photo Z that we get and the spec Z that we get. It's not too bad. And it has been improving month by month. This is originally a plot of the 0.03%, the number of galaxies that you get at the time, the cumulative fraction. This was in April. In September, it had already grown to this. And in October, and we're talking not this year, we're talking almost 2019. So this was already at the 50% level. So techniques for calibrating and improving the redshift can go a long way. So we are at the target. This is actually, we're looking at the universe through a little hole, a little window. This window has 1 square degree, but you can go all the way. This is redshift here. This is the position, RA, and those are galaxies that you see. And you can see the mini Jpes is in yellow here. The deep 2, who has real spectroscopy, is in blue. And you can see all the walls, the large-scale structure. We are perforating this large-scale structure all the way to high Z's, right? So this is a pretty good match. Oh, this is, thanks, Chairman Diego, one of the coordinators for the Cluster of Galaxy Science Working Group, has done this just for fun. This is not as long as the other one, so you're not going to be so bored. This is we are just walking through that line, increasing in redshift, and seeing the structures weight by light. Okay, what you'd see there. Okay, so this is nice. And one of the things that is very interesting to me, and I guess to the cosmologists as well, is that it's not just BEO that you measure. You can do constrained cosmological parameters doing other things, for example, cluster count, and actually many other things, including the large-scale structure itself. So Jpes will be able to do this as well. So you all know that in the case of clusters, for example, that by knowing the mass function of clusters, the number of clusters of particular mass over a certain redshift, this is a very old and classic thing, the classic paper from Borgani. Those 3 universes here, they're extremely discrepant. There's omega meta and omega lambda, 1, 0, 0, 0.3, 0.7, 0, 3, and 0. But you know that this can discriminate what kind of universe it lives in. Of course, nowadays you need something way more precise than that to do it, but that's the idea. And if you see the evolution of the mass function with redshift, you can get information about the dark energy. So this is one of the differentials of Jpes with respect to all of this, the optical surveys. Since we can get a large number of objects, and you can, since the redshift is so precise, you can get them their position. We can get their structure down to very low masses, like groups of galaxies, because you know you can measure the redshift difference between the galaxies and be pretty much certain that they form a system. They are gravitationally bound to each other. So there's a comparison. Begonia-Scaso did in 2015. There was a prediction at the time for the limiting mass of systems that we could get. Very high mass, they're very nice. People do it. They're not extremely very common, and they grow with time. So they become more massive as you get closer to today. So if you go far back, you really would like to get the low mass systems as well. And this is the Atacama Cosmology Telescope, and this is the South Pole Telescope, eRosita, DES, and SST, and Jpes is right here. And none of them get even close to the masses that Jpes can get. And notice that this mass here was artificially stopped, okay, at 10 to the 13, a few times 10 to the 13. The only one that gets close to that is eRosita. And we actually have an agreement with eRosita, and it's going to be very useful to study groups at intermediate redshift, something that is quite new as well. Because we don't know, one of the things that's very important in cosmology is the, I'm sorry, just 1 second. Just 1 second. Sorry for that. Where was I? Yes. So we know that the scaling relations that we know for big clusters allow us to look at just the galaxies and be able to get the mass at very high redshift. But we don't. We suspect there are many indications that for groups it's different, and we're going to be able to measure them. This is a plot of the number of systems with redshift. Again, Jpes, SST, Rosita, DES, and South Pole Telescope. Jpes is going to have more systems up to 1 than an SST. And we get a very nice match with Rosita here as well. So this is already the data. For the mini Jpes, okay, that's the level of completeness. I'm not going to enter the detail here, but this is the clusters that have been in groups that have been detected in the mini Jpes, in that 1 degree field that has been covered, mapped by X-rays, and X-rays can give you an idea of the mass. Of course, it's not very deep, the X-ray that is there, Chandra, and a little bit XMM. We're going to submit another proposal for XMM next week, actually, to try to cover this a little better. The error bars are still pretty big. But you can see this is the redshift here. That's the mass and 10 to the 14 solar masses. You can see that we get down to 10 to the 13 easily, and some of them before that. Okay, some of them you can get to 10 to the 13 at redshift of 0.7 or 0.8, and this is really amazing. This one here is that big cluster that I showed you before. This is an anomaly, the most massive one. So with this, Matteo Maturi is about to submit the results for the cluster catalog using his particular code. We have 3 different codes being tested. One of them is the Amico code, is a matched filter code that's used by Euclid. The other one is PZ Wave, which is a wavelet, variant of this that is used by Gonzalez in the University of Florida, and somebody in Jpes is implementing them. That has really great results. And also the Van Light tessellation code. There's in development is giving significantly closer to the other one results. And Paulo Lopez is the person who is doing this mostly. So this allows us to do some of the scaling relations. This here uses odds at about signal to noise of 2.5 and 3. So if you be strict, if you have numbers, you can be strict as much as you want. This is signal to noise to 3, and this is clusters about more than 0.56 in red here, 0.25, 0.56 is in blue, and those ones are less than the nearby, less than 0.25. And you can get some scaling relations working here. Notice that we have only 1 square degree. Okay, so this is not Jpes will have 8,000 times more that. So, but in any case, it's pretty amazing that we can do this. This is a map of the Amico code. It's very sensitive to the change in the density, projected density with the background. And this is some of the clusters it has detected. Those are X-ray contours obtained with Chandra. So the other code that we just got some of the results a week ago, the PZ wave is actually very impressive too. This is the same field, but those are Chandra pointings, okay? But Lia Dubrava is leading this work. And this is the mass and the redshift here and the ages with X-rays. And without X-rays, because the X-ray is not very deep, they're also there. We would like to see if they're real or not. X-rays basically make the system real. But you can see that this is 10 to the 13. So you can get, even though at ratio of 0.7, you can get things at 2 point something times 10 to the 13. It's pretty impressive. So we're going to get there. One of the consequences of this, of getting to the low mass regime, is that you can actually map the filamentary structure of the universe. You can have the nuts, the small little nuts, and you can actually use, this is a simulation of millennium, just for illustration. You can use, if this is a cluster, for example, you can see the groups would be smaller nodes. And then you can map this, and you can make a very nice 3D map up to 9 billion light years with Jpes. And you can use the filaments themselves as priors to improve the precision of the photo Z. And this is a work that is being done by Taku Kitaura, and has been planned to be done. This is just an example of a very low mass system at 0.23. Okay, so this is 10 to the 2.9 times 13, so it's not that low actually. And this is again the one that I showed in the beginning, the cluster that is the most massive one. So the interesting thing with Jpes is that you don't get just the cluster. By the way, the contours here, the red is the equivalent to the weak lensing, what you'd see, and the blue is the X-ray contours from XMM. So, but here you can get not just the system and get the richness and get the mass, but you can also look at the galaxies in the cluster because you get everything at once. And there's several people doing it. There's like 3 papers, Raza, Orduriz Martin. There are 2 already published, looking at the age of galaxies. This is mass by color, this is mass by color, and this is the equivalent width of H alpha, okay, using artificial neural networks. Because with ANN, you can actually get amazingly good results for that, even though the spectrum has a resolution of 60, right? So you can see the red galaxies, the red ones and the blue ones, they're active or not, and you can characterize the cluster by doing this, and you can do this for the whole sample and to characterize the evolution of galaxies between different slices of redshift. There's 0.6 to 1, 0.35 to 0.6, 0 to 0.35, and you can see different populations here. This is the age in 10 to the 9 years. And you can study the galaxies this way. Okay, Martinez Solace, 2020 is already there, 2021, and so on. So this is another bonus for Jpes. And of course, you have forecasts for different things, and maybe some of them should actually be redone now. They have real data. This is one of the first ones for using cluster counts, like I mentioned to you in the very beginning, with 8,000 square degrees and so on, and had a theory of merit of 190. That's WA, W0, as a count that the variation and the time variation and W0. That's the size of errors that one could get. There's actually probably an interesting idea to redo it. And several papers more recent, the theory group in Jpes, which is led by Jailson and Antonio Marotto. They have produced us many papers now for different forecasts. This one is the recent one is for this is modified gravity, and mu0, if I'm not mistaken, here is the effective G, and at the 0 is a ratio they call slipping function or gravitational slip, if I'm not mistaken. But they characterize different modified gravity models, and they can clearly separate. This is 0. This is can separate one case from another. And on top of that, this is WA/W0 I showed you before, and they compare this with Euclid, DESI, and Jpes with halfway, 4,000 degrees, and Jpes with 8,500 degrees. And so Jpes will measure W0 in this case here for precision below 6%. They can be compared with DESI for 4.5% and Euclid 3%. So Jpes is competitive and complementary to that. And you can also get the other astrophysics. And just citing here, I'm not going to enter in details about the other testing forecasts that have been published. Some of them that have interacting dark matter, dark energy. Without, this is with, I guess this is with momentum transfer. The other one is without momentum transfer, and they have their different forecasts. I recommend anybody that wants to take a look at this, or I can send the reference, or Jailson could. So the synergies that Jpes has with other surveys, because now we have a real interesting, not just redshift machine, it was intended originally, but also a J spectrum, a spectrum that you can study the chemistry, evolution, and so on in a pretty wide range of redshifts. And so we were approached some of the other missions that are going there, and we have some agreements with them. One of them that we're just closing now, kind of already closed, but we don't have yet an MOU, but have an agreement, is one of the other fields that had been observed by the Pathfinder, the camera that I showed you before, the Jpes, which was another pointing with all the filters for the North Ecliptic Pole, the NAP. The NAP is very interesting because it's the galactic pole of the galaxy by itself. It has low, absorption and reddening and internal from us. And you have on top of that, it is also one of the points that JWST will be able to be continuously monitoring. JWST is this new Hubble, basically, super mega Hubble that will be launched in a month, 2 months. And they have, this group has a GTO, guaranteed time observing for the field, and the magnitudes that are ridiculous. They go to 28, 29, is amazing. But since the JWST is going to be observing this continuously, it can do time domain studies, supernova, things that vary, very quasars and everything that can vary there, bursts of any kind. So this is the website, in case you're interested. We have a joint program with them. The other one that we already have an MOU written is with eROSITA, which probably some of you know is this all-sky X-ray survey. We have an agreement with the German side of eROSITA for now. And they overlap. This is the region. This is the German sides. The Germans have one side of the sky, and the Russians have the side of the sky. So we intercept with the Germans on this side of the sky, so we are going to be doing a lot of work with them. eROSITA is going to the third year. So at the fourth year, they get to the maximum scanning depth. And we also have an agreement with Weave Jpes. Weave is using fibers. They get real spectra, as you like to call it. And especially for the group of quasars. For the group of quasars, they approached us because they're going to be doing cosmology with quasars. We life and alpha absorbers, they go to redshifts like 3 or 4. So really, really far away objects. And Jpes has one advantage with Weave. If you look at here, this is the density, the evolution of average density of galaxies with redshift. The solid lines here, they're Jpes, and the dashed are DESI. DESI is a fiber. It's very, very good, supposed to be a very good survey. So they beat a higher Z's. They can have a higher number, and the higher number, you get better statistics. You can do all the tests you want to do with getting higher precision. And this is using the luminous rare galaxies. Those are ellipticals. And green is using emission line galaxies, spirals, blue galaxies. And so they take over when they get to redshift about 0.8, 0.9, and they go to this zone that we cannot go there. However, if you look at the quasars that we got, and I showed you some in the movie, at 4.3 and so on, they stay here, down here. And Jpes can go all the way to very high redshifts. And that's a very good advantage. And that's what the Weave QSO survey wants to do as well. But they use fibers, which means you have to know that that thing is a quasar before you look for the object. So that is a problem, right? So there's going to be a lot of misses, hits and misses like crazy. So Jpes has an agreement they're going to pass first before they come in. And with the J spectrum, you can tell if the source is a quasar or not, and then tell them where the quasars are. With this, you can increase by like 30%, perhaps more. Can get to several million of this Lyman alpha systems and quasars, okay. And this would allow them to, this is the fractional BAO error with the Hubble function, this with the angular size distance. And let me see, this is not very clear, but the DASI goes up to here, and then the error just explodes very soon at 3. And the QSO with Jpes can go all the way to 0.36 or 3.6 near 3.8 in redshift. And this, with this number of quasars, you can actually see the BAO at very high redshifts. So I'm getting close to, I have still 3 minutes, I guess. So the first, that camera, Pathfinder, is out, has been out for a while. And the new camera came in, the big one came in. The first technical light was in June 29th, 2020, which unfortunately was right when the pandemic got really bad, and things got complicated to move, to do things, and that caused some delay. This is a technical light. They did not even do the actual first science light, because there was no time to do it. And this is Andromeda Galaxy. Just to have an idea of the field of view of the JP cam, this is the moon, okay, on this. So just to sum up, so Jpes all sky, we call IFO, this over here. Okay, so, sorry. So it's many thousand, more than 8,000 square degree survey with 54 contiguous narrowband filters of 100 spaced by 100 angstroms, covering the full optical spectrum. There are 2 medium band filters one covering the near ultraviolet and the other one the near infrared. 3 broadbands covering the full optical range. The site is very dark. The scene has been tested many times. It's pretty good for years now, for decades actually. The 2.5 meter telescope, 4.7 square degree camera. It will measure 0.3% photo Z for about 100. The better number is like predicted 90 million galaxies. For redshifts, they go from 1 to a little bit more than 1.3, 1.4 perhaps. 500 million galaxies with 3% photo Z, which is not bad by itself. Not for the particular BAO, but for many other things, this is not bad. Several million quasars with 0.3% photo Z. With the weave, we're going to be able to get BAOs of more than redshift of 3, 0.8 arcsecond image of the northern sky, very sensitive optical cluster catalog, getting down to masses of less than 10 to the 13. And there's going to be a survey of supernova. It's not clear yet how the cadence will go. And this is something that's being discussed, but the original plan was to get a few thousand supernova and immediately have a characterization of the host of the supernova when you get that. So the radial bounce for galaxies up to 1 or a little bit more than 1 in redshift. So in numbers, we're talking here about big clusters, 100,000. If you get groups, you're going to get groups and clusters going to be 500,000. Weak lensing map of the sky, thousands of supernova, and a few million quasars, and those numbers, asteroids, stars, and so on. So this is the day that the camera got in the telescope, and just see a bunch of people very happy there. So I guess I'm going to stop here, and thank you.
Okay, thanks a lot, Renato, for this very nice and very clear talk about Jpes. I'm going to open for questions. If you have any question in the audience, please let me know. Yes, Saulo. Okay, Saulo has to. Okay, Saulo. I think you can.
Okay,
yes, go ahead. And then Fernando.
Renato, thank you so much for the nice talk. Have you talked about the synergy between the different surveys? And but of course, I think Brazilian and Spanish are also worried about our capacity to compete with other surveys like DESI and Euclid. You have shown that we are competitive with almost the same precision. Actually, for low Z, we have a better precision, I think. But all depends on the timing. So my question is, how is our timing now in this run, in this competition with the other big surveys of this generation?
Yeah, so the timing, I cannot tell exactly how our timing is yet, but we are at the middle, don't know if middle end or middle of the commissioning of the telescope. DESI is going to be more efficient, in terms of numbers in the first few years. So with DESI, I don't think we compete directly at the BAO at low redshift, but like I mentioned before, if our synergy with Weave works, and everything is okay with Weave, because they are also a little bit delayed, which is kind of good, for us. So we can, in terms of competition, we can always complement DESI, right? So it's a great complementary system, but we can be more competitive probably at the BAOs at very high redshift. So with respect to Euclid, there are different things, right? I'm not sure exactly how they're going to compete directly in how Euclid is going. I think it's going to probably be not as late as we are. So I cannot tell you with great confidence how we are comparing the two surveys. But in our case, if everything goes okay, we should finish the telescope. The camera is going to be re-cooled down in about a few weeks, maybe a couple of weeks, and start getting cool again and continue commissioning. Hopefully in a few months, we can finish the commissioning and start collecting real data. Now, the speed of the survey is something that is always better to say once you see the weather and things like this. Jpes, for example, was supposed to be in the beginning. Well, Jpes, I'm sorry, mini Jpes was supposed to be in the beginning much faster than it actually was, because it was based on the weather patterns using Jpes for the site. But it happened that 1 year, the weather was just very bad. And so because of the cold, they delayed basically 1 year because of that. So it's very difficult to say. Things in space don't have this issue. But hopefully we can in the beginning of next year. I'm optimistic that we're going to start collecting a significant number of data. And that depends on how it's going to grow. Probably it's going to be about 1,000 degrees per year for most filters.
Okay. Rogério.
Renato, thank you for the very nice talk. I have two quick questions. One is, how many people are involved in Jpes from Brazil and from Spain? And the other is, since you have images, are you considering doing weak gravitational lensing studies?
Yes. Okay, first question. Right now we have about 200 members. If we include also postdocs and students, perhaps a little more. In Jpes, I'm not sure exactly what's the percentage for just the members from the different countries, but I would say that it could be, because it's not just Brazil and Spain, right? You have people from different countries. You have people from Italy, from Portugal, from the US, and have many different members. So, but in terms of the organizational structure, I think we have about 50-50, Brazil and Spain. The science directors and the coordinators of the science working groups have theory, cluster of galaxies, large scale structure, resolve stellar populations, and you have galaxy evolution, and have even transients, which includes the asteroids and so on. So it's about 50-50 this. And this is from us. And it's not just the 4 institutions. There are people from different institutions that can be coordinators as well. So in your second question, yes, and there is a lot of effort to do lensing. Some of the results appearing, but certainly weak lensing is going to be done. I'm not sure if it's going to be like pointing at particular clusters that you want, or if it's going to be as of stacking clusters, it's going to be definitely possible to do it. Strong lensing, of course. But if you talk about shear, cosmic shear, that is theoretical. This is possible, but I don't think we have a group yet. We don't have a particular set of specialists. There are very few people that actually can do this in the world. We have members. They're members, but they are busy with other things, and we don't have a lot of effort yet on that.
Thank you, Renato. Yes, shear is very difficult. I agree.
Okay, more questions? Okay, if you don't have further question, I'm gonna end this session by thanking Renato again for having accepted our invitation for this very nice, very clear talk.
Thank you.
Okay, and okay, so this is the last talk of the day. We will be back tomorrow at 9, I guess. Let me check here. Yes, at 10. Tomorrow we start at 10 with PA05 and PA06. So good night, everyone. Renato, thank you again.
Thanks. Bye-bye.
Bye.